last class we looked at this particular case of x plus y in some detail, right. But of course you can define, starting with x and y, which are for the time being they are discrete, you can define any kind of combination which makes sense or which is important in some situation or the other. I have given a few examples up there. X minus y is as sometimes as useful as x plus y, or max, min, and so on, right. Remember, max and min slightly different from x and y in that you may have to work a little harder to understand it, or it's just the larger of the two, right, and min is the smaller of the two, that is all. And they are all discrete random variables when x and y are discrete. We are giving a name only, as of now we are giving a name only to x plus y, which we are calling z. Later on, maybe during this lecture I will work with some one or two of the others, and we can give some names at that point, right. So as of now we have z equal to x plus y, and we pointed out that we could get the PMF of z, or any one of them, of any of the derived random variable. What are the two steps? The first step is to determine omega for that random variable. For z, let us say. So you must determine the range in which, or the set of numbers in which z takes values, and then the second step of course is to determine the probability that z takes some value in that set. So you have to do this for all possible values in omega z, only then the PMF is complete. And how do you do this? You just look at what combinations of x and y give you that particular value of w, and the joint distribution of x and y will automatically tell you what the joint probability is, and that joint probability is inherited by z. The summations, if any, occur only when you have multiple points in omega xy which map to that particular value w. So why did we get a summation in the convolution case? The convolution summation came about because you have, when x and y are integer valued, you have many combinations of x and y which give you a particular integer value of z. For example, if you throw two dice and say z equal to x plus y, you can get for example omega z will be 2 to 12, that is obvious, and then but any number like 6 or 7 or 8 will have lots of combinations of x and y which give you that particular z, right. 3 and 3 will give you 6, 4 and 2 will also give you 6, 2 and 4 will give 6, etc., etc. So all of those probabilities will have to be added to get the probability of z being 6 or 7, whatever, and then you can easily verify the convolution, right, result even without going into convolution. It is just a nice triangular or sort of pseudo trapezoidal in the sense, no, it is triangular, right. Pz in this die roll case 7 has the maximum probability, right, the sum. Anyway, so I think I am not going to repeat what I said last week. Beyond this, we have to move on to something different. So today what we will do is to take the case of dependent x and y, right, not independent. And the simplest example would be x and y are jointly trinomial with parameters capital N, P, Q. This is I think the notation is fairly obvious, right. P is the count, event count for x, and Q is the probability of the event count for y, exactly like we have done earlier, right. No, there is no change in notation. Capital N is what we used earlier. Okay. So we already know the answer to this, right. So if I say, if I look at x plus y, it is basically the sum of the two counts. So it has to be what? You are basically putting both in a single box. So do we know the answer to this or not? what is right? What is x plus y going to represent in the trinomial case? X plus y is going to represent the count of either the event 1 or the event 2. And remember we said those events have to be exclusive, otherwise it is not trinomial, isn't it? So x plus y must be binomial with parameters n and p plus q. This we know. N can never increase because you have a total of n trials, or n times you are throwing n balls you are throwing into bins, right? You do not have more than that. So you cannot get 2n or any such thing. So that so it has to be limited by this n, but the probability of that box would become bigger and it will become p plus q, because you are looking at either the first event or the second event. You are not really distinguishing between the two, you know. So this is the count that you get either event 1 or event 2, right. So how do we derive this? So this is what can I say, this for the sake of the camera I have to say that it is, I put some text down here on the board. Shall I put obvious, put question mark? Anyway, but let us just derive it and see for ourselves what it, you know, that we do in fact get it. Now I think what I have to do here is I have to go here and write the expression. This pxy of, let me see what notation, I comma j, right, I used? Okay, I comma j is n choose I, n minus I choose j, p to the power of I, q to the power of j, 1 minus p to the power 1 minus p minus q to the power of n minus I minus j. So this for 0 less than I comma j less than n, I plus j is also strictly okay, is less than equal to n. So this is basically our starting PMF. So here x and y are both integer valued. So what is, right, what is omega z? So I am going to check this result. Omega z is what? Both x and y need not happen at all. So obviously z can also start from 0, or both x and y can be 0. So omega z starts from 0 and goes all the way up to n. Cannot be more than n, right. We have already said, right, the x plus sorry, you are repeating the experiment n times, and so the count of the two events that, for which x and y are the counts, the sum cannot be more than n. Okay, anyway, so therefore z is also integer valued and takes values only in this set. So what is pz of k now? So what I have to do is I will write the expression down, pxy of I comma k minus I. This anyway I have, right, this is what I have to start with. So for a particular value of k, right, I can, x can be I and y can be k minus I. What will be the range of I in the summation now? We have already done this for the Poisson case, right. So this is exactly the same thing, the limits are very similar, right. So again I go from 0 to k. Remember we are looking at the probability that z equal to k. So if z is k, x cannot be more than k, x can be at most k, isn't it? But here, because they are dependent, this cannot and will not factorize into px of I into py of k minus I. That is the most important difference between that and this. So let me just put down some key, just the key manipulations here, just to make sure I do not waste time. So let me also draw this diagram out here. So what I am doing is, this is the n, if I draw this as I and j, this is the point n0 and this is the point 0 comma n. So the k will be some line parallel to this. So this will be the point k comma 0 and this is 0 comma k. and you're going up and down this line. So this line corresponds to, let me say, z equal to k. Z equal to k is the same as x plus y equal to k, right? Okay, so so you're basically taking some point on this line and adding up all the you're taking this line for that value of k and adding up all the points that fall on that line, the probabilities of all the points that lie on this line. So you can easily do this. I'm not going to spend too much time on this because manipulation is not very convenient on the board, but let me just write some key steps. So if I do this I equal to 0 to k, just simply I have to substitute this out there, n choose I, n minus I, choose k minus I, p to the power of I, q to the power of k minus I, 1 minus p minus q to the power of n minus I minus k minus I. Remember, all I am doing is substituting k minus I for j. And then so I have here p by q power I. This q power k can come out n factorial. So essentially what I will get will be, let me just skip some steps and write this. So n factorial divided by n minus k factorial q power k Hmm. 1 minus p minus q to the power of n minus k by k factorial times summation I equal to 0 to k, this will be just k choose I, p by q whole power I. I want you to work this out. It's not, I don't think it's too much to ask. Just expand out this factorial, so expand out both factorials and I mean both this thing binomial coefficients and write it like this. And you can clear what is that summation. We have seen this type of thing earlier. It is just 1 plus p by q whole power, what is it, whole power k. So I think you can easily show from all of this that this will become equal to what? This becomes equal to n choose k, I'll draw a line here, n choose k p plus q to the power of k 1 minus p minus q to the power of n minus k. The point is this 1 minus p power n minus q, this thing has already come here itself. So this just gets repeated here. So what is this? This is valid for all k. We have not said, right, we have not put any condition on k. So this is true for k equal to 0 up to capital N. That is as you move this line all the way from this point to here. What is that PMF? Binomial with parameters capital N and p plus q. So this is an example of a dependent sum calculated, PMF calculated from first principles. So the same thing you should be ready to do. Of course, we don't have any, I mean other, as I said, all other examples that I have seen of joint PMFs are more contrived, right? Only this trinomial thing seems to be the in a sense the most acceptable thing, you know. All others look like they're more textbook examples than anything else, but unlike this. Anyhow, so this example I think should illustrate the point. Let me not spend too much time on this. Is there any question here? So I put a tick mark here to say that this is what we wanted. This exactly matches this. Okay. What about x minus y? Remember, right now we will give some name to x minus y. Now consider, I am not going to spend too much time on this, x minus y. u, when x and y are integer valued, u is also integer valued, but it can also now take on negative values as opposed to only positive values when x and y, even if x and y are both positive, right. Okay, u is or so, but u can be less than 0 as well. So, for example, if you take the difference of two die rolls, how will you go about finding the probability that u equals -1? It is the same principle. You look at combinations of x and y which give you -1 and all those things, right. So, it turns out that actually so, let us take this case of u integer valued, right. It turns out that p u of k is the double summation over the I of interest p x y. If I put I here, I must put I minus k here. Why I minus k? Because this difference is what? Is k, but k can be positive or negative. Sometimes you have a symmetry in this situation, and you may find that it is enough to calculate for positive k, and then for example in die rolls the difference pu of +1 will be equal to pu of -1. Well, may not be, I mean no, I don't know, I take that back, I haven't checked it out thoroughly, right. But this in general again uses the point is that it uses this discrete it uses this joint PMF, which is the key. Without the joint PMF in general, what I want to say is you cannot proceed. Of course, in the independent case what happens, it will factor into pu of I into py of px of I into py of I minus k. So, then this factorization happens for independent, right. And then you get, what is that operation called on the two sequences px and py? Have you seen this in your DSP class? It is correlation. So, only if you get this, you get the correlation of the PMF. So, for integer valued sum, independent sum, you get convolution. For integer valued difference, you get correlation. Okay, so let me not I am not going to work, I mean this kind of manipulation is best left to a homework exercise. I am not going to do any example here. Just want to point out one thing though, what is pu of 0? Pu of 0 has some significance. Pu of 0 is basically identical to the probability that x equals y, right. These two events u equal to 0 is identical to the probability that x will equal y. So, they are no different. Now, the next thing I will quickly look at is the max and the min, but I am not going to look at the dependent case because the dependent case is like the trinomial is very messy to handle. We will look at the independent case. Pardon me?
Can you repeat this concept?
Which part?
You equal to x minus y. What is, does it denote number of times events one happens?
Okay, u equals x minus y is just the difference between the count x, the value taken by x and the value taken by y. So, on a trial if you find we roll 2 dice for example, right, you get 3 on one, 3 for x and 4 for y, you will take the value -1. That is all. In the trinomial case, right, if you are looking at x and y as the count of 1 and the count of 5 on n rolls of a die, again you can look at the difference. So, the number of times you get 1 minus the number of times you get 5 is u. This is okay. Please ask, right? Do not hesitate to ask. If any question is okay, right? And this is clear that Pu of 0 must be P of x equal to y. When do you get u equal to 0? Only when x equals y, if and only if. Right? So whenever x and y take some two values, you will take a value. And a value which is uniquely determined by the values of x and value of y. So that concept is so important that I have to repeat it several times. That is, x and y jointly determine everything about the derived random variables, right? Everything from the set in which the derived random variables can take values to exact values on trials, the whole thing, right? So derived is completely something which is based only on the existence of u, z, whatever else you might want to define like max, min and so on. All of them are defined based on the underlying x and y. It's a kind of processing you do, right? Like you receive x and y, you process x and y in the way in which you want to do it, and then you derive whatever. Is this okay? Now to nail home that point even further, let us look at max and min, as I just now said, but I am not going to do it for the dependent case because dependent case is messy and I won't try. I tried writing it here, and I mean I've done it in the past, but it's not been very nice to work with it. So let me take this as a as a test case. So now I am going to take x and y are independent integer valued. So first of all, what do you understand by max x y? So how do I determine v from x y? So v equals x, i.e. when do you say it is x? When x is greater than y, otherwise you set y. This is the meaning of max, exactly like you have for any two numbers. You can always take the maximum of two numbers. So you can take the maximum of two random variables also. So ouch, this is it's okay, doesn't matter. Okay, so we are also assuming that they are independent and integer valued. So if they are integer valued, you obviously v also has to be integer valued. Now let me take what example did I come prepared with to discuss? Okay, just doesn't matter. Let it be just any integer value, doesn't matter. So what is right? So omega v is also a set of integers. Now not the full set or the sub. So the value this so what the minimum of value of x is the minimum value of either x or right. What would you say it is? Whatever. I mean, if both x and y start from 0, then the minimum can be 0. If x is, starts from 0 and y starts from 2, obviously the minimum cannot be, the maximum cannot be 0. It has to be 2. So you have to determine this omega v appropriately, right? So let me not write any notation on this. So I want to look at just the probability. So this has to be done. So this needs to be done, to be found, right, on a case by case basis. So now I just want to write an expression for PV of k, right, for the integer valued case. So what is PV of k? You get k when what do you get when x, let us say x takes the value k, then y must be maximum k, right, or y can be k and x can be smaller than k, but you shouldn't count anything twice. So it turns out that PV of k is basically the probability that x equals k, y is less than equal to k. Okay, fine, this is one part of it, which is fine. So note that whenever this happens, the maximum will be k plus p, the probability that x is only smaller than k, because I have already looked at the equals case here. So to avoid double counting, I have to insist that x is smaller than k when y equals k. I do not want to count p x equal to k, y equal to k twice. So this is true even when x and y are dependent, right? This does not require independence. This is always true. In the independent case, what can you, how does it simplify? These are now joint probabilities involving x and y. But when x and y are independent, then this event x equal to k becomes independent of the event y less than k. So this becomes so this manipulation, I am just simply writing it. I am not going to go go further with this. I think it's best left to a homework exercise at this point, because right doing extensive manipulations on the board is not very conducive to an interesting class, I think. So we will leave it at this. Once you get any problem down to this level, it's easy to do, right? Because especially if you have events involving only one random variable, you can easily find this, right? I hope this is not a problem for anybody. P y less than equal to k. In fact, with this kind of thing we'll use a lot in the continuous random variable case.